lesson on applied optimization problems. And we're going to do a lot of examples. It's going to take a while, but I think you're going to see some actual use to some of the techniques that we've been kind of going over in this section on applications of differentiation or derivatives. So I'm going to start off with this first one, right? And this first one is talking about maximizing the area of a garden. So the figure is very helpful. You'll notice that we have a rock wall on one side, so we don't need to worry about any wire fencing on that side. But we do need to have wire fencing on the other three sides. So they've gone ahead and told us that we're going to use the letter X to represent the sides that are perpendicular to the rock wall side, and the letter Y is the side that is parallel or across from the side of the rock wall. Now, we want to maximize the area in terms of this garden, but we can't just like keep using infinite number of or larger dimensions for the fencing, because we do have a constraint. All right, and that constraint is that we only have 100 feet of wire fencing. So the first thing I'm going to do is write down my area formula, right, which is going to be length times width. So in this case, X times Y. All right, so that's the area for this garden. Okay. However, when I look at that, you'll notice that we have a constraint that deals with the total amount of wire fencing in feet. And so that's where I'm going to think of the perimeter, all right, which is adding up all the sides, the side lengths around the rectangle, all right? But in this case, you'll notice a little different. We have two of the X ones, right, with two X's, but we only have one Y that we need to worry about, all right, because ultimately the rock wall is going to serve as one of our other sides. So we only have to worry about one side length for Y. And this has to be equal to 100. Okay, so what I did here is the next step is to isolate Y. All right, so Y equals 100 minus 2x, moving 2x over. And now I'm going to substitute this letter Y, which equals 100 minus 2x, into this letter Y. So I'm going to rewrite my area as a new function that is now x times 100 minus 2x, or 100x minus 2x squared. Okay, I'm going to pause here because this is ultimately the area function that I want to maximize. So I'm going to find the maximum on this of this function using some of the strategies we used in earlier lessons. But before I do that, I just want to take a moment and you want to think about what your possible values for x could be. All right, so think back to the very beginning of this problem where we said we had 100 feet of total fencing. All right, so if I make x equal to 20, right? So 20 times 2 is 40. 100 minus 40, y is 60 feet. Okay, so the idea is that whatever you make y and whatever you make x, right, they're going to have to balance off each other to make this equation true. So you can't just say, oh, x is 1,000, right, because that won't make any sense. Because they need to be positive numbers, right? We can't have negative lengths of fence, right? We can't have an x value that's greater than 50. If our x value was 51, then our y value would be a negative. So we can't have an x value that's greater than 50. And if I use ultimately for my y values, I don't want to have a number that's greater than, I think, 25, because ultimately if we do something larger than that, then our x would have to be end up being too large as well. Okay, so just keep that in mind before you kind of do the strategy here. So I'm going to write down the area function. All right, it was 100x minus 2x squared. So what I'm going to do is I'm going to take the derivative of that. Okay, so that's going to be 100 minus 4x. All right, and that means we're going to have our critical points. We're going to have we're going to have our critical points are going to make it equal to 0. Nothing's going to make this undefined. I should have said that I want to find the maximum of this area function on the bounded interval between 0 and 50. That was the whole point of that discussion about the possible x values. Can't have an x value more than 50, otherwise our y value would be negative. So if I plug in my endpoints, let me do that actually first real quick. So let's plug in the endpoints. I'll do the derivative here in a second. So if I plug in my endpoints, I get 100 times 0 minus 2 times 0 squared. That's going to be 0. This is I got 100 times 50 minus 2 times 50 squared. All right. I don't actually know what that is, but if you plug in a calculator, you end up getting 0 as well. All right, so both of the endpoints happen to be 0. It doesn't matter that they're the same, but now I care about finding the critical values, which is going to be that derivative again, 100 minus 4x, set it equal to 0. Okay, 100 equals 4x, or x equals 25. So an x value of 25 would maximize the garden area, all right, and keep us in the constraints of that we only have 100 feet of wiring to use. All right, it also says what is the area. So I'm going to plug in 25 into the area function. All right, and then you can go to Desmos or find that it's 1,250 square feet. All right, now I left this other slide here blank because I'm going to show you what happens when you sketch it. All right, I'm going to go to Desmos and sketch this area function, 100x minus 2x squared. All right, so we have 100x minus 2x squared. All right, I'm going to make a table. That way I can zoom fit. And we care about, let me get the zoom there. There we go. Okay, so we care about having our highest y value is 50. There we go. And then we also need to have 25 in there, right? That is our, there we go. That's our maximum. So you'll notice we have 0, 50. Those are the endpoints. And we said our critical point was 25. And that is where we have our highest y value of 1,250 square feet. All right, so you can see how Desmos allows you to find this as well. But ultimately, I want you to focus on finding the critical points, not just using the Desmos. Okay, so ultimately, Desmos, just if you want to put a sketch, you can. But I left this slide here blank in case you wanted to sketch it. Okay, so that's it for the first one. I'm going to move into some more optimization problems focused on this problem-solving strategy. Okay, so for this next question, we're going to be talking about maximizing the volume of a box. So if an open-top box is to be made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side, what size square should be cut out of each corner to get a box with a maximum volume? So I'm going to draw two things. First thing I'm going to draw is our cardboard box that we're using. So we have 24 inches by 36 inches. And then I'm going to draw what's going to happen when you actually cut out these little tiny squares in each corner, which I'll label with X by X, right? Their lengths, side lengths will be the same. All right, so I'm going to draw, let's see, we'll have, again, doesn't need to be like a great drawing here, but the idea is that we're going to be having a box that's being cut out here. So we'll have, let me actually draw it a different way because that might be a little confusing. So give me 1 second. Let me make sure I know how I want to draw this. Okay, so let me try it like this. So I'm going to draw these together, something like that. Okay, I think that's, well, I'll go with that. Not very good, but this is my height. This is my width, so 24 minus 2x inches, and my length is 36 minus 2x inches. Very similar to my my width, right? And ultimately, this is about maximizing the volume. So the first thing I'm going to do is write down the volume, which is length times width times height. So this is going to be 36 minus 2x inches times 24 minus 2x inches times the height, which is whatever height we choose for the squares that we're cutting out. Okay? Now I'm going to multiply this all out over here on this side. All right? So that's going to be 36 times 24. We definitely need a calculator for this. So 36 times 24 is 864. Okay, then 36 times negative 2x is negative 72x. Negative 2x times 48 is negative 4, or negative 2x times 24 is negative 48x. Then we have positive 4x squared. Now that's not everything because we need to multiply that by x. Let me simplify first. So 864 minus, let's see, 72 plus 48 is 120 plus 4x squared, and then times x. So I'm going to get, I write in standard form, 4x cubed minus 120x squared plus 864x. So this is my equation for volume, all right? And ultimately, when I look at kind of that discussion that we had with the previous problem, before I find the critical points, I want to think about what's going to be my interval here in terms of what I'm looking at for my values of x, because I can't just make x whatever I want. Excuse me. So in this case, if you think about it, right, the width is 24 inches. So if I cut out 1 inch, 2 inch, 3 inch squares, whatever I end up cutting. But if I cut more than half of it, right, if I cut 13 inches, then I don't have enough material on the backside, right, to have the same amount of cardboard cut out, right? So I have to have less than 12. So when I look at, in terms of my bounded interval, I'm going to be looking at between 0 and 12, all right? So I'm going to start out by plugging in the endpoints, right? So plug in 0. Obviously, that's going to be 0. Plug in 12. So that's going to be 4 times 12 cubed minus 120 times 12 squared plus 864 times 12. Now, I'm going to do it on my phone next to me real quick, but you know, with a lot of these, it'll end up being 0, but you should take the time to see if it actually will be 0. So that's going to be 12 cubed times 4 minus 120 times 144, and then plus 864 times 12, and you get 0. Okay, so also getting 0 means that when I look at the sketch of this over this bounded interval, then I'm looking for the absolute maximum between x values of 0 and 12. So I'm going to take the derivative. Okay, so my derivative of volume is going to be 12x squared minus 240x plus 864. Okay? Now, you may not see this, but you can actually divide all three of these numbers by 12. So I'm going to write down my derivative is 12 times x squared. 240 divided by 12 is 20. And then 864 divided by 12 is 72. Now, unfortunately, there are not factors of 72 that add to negative 20. So you would have to either use the quadratic formula or you could complete the square. Just because I absolutely love completing the square, I'm going to. So I'm going to move this over, get negative 72. Oh my gosh, it's been so many years since you've done this. So you have b over 2 squared, which is going to be negative 10 squared, which is 100. So I'm going to add 100 to both sides. This is going to factor to x minus 10 squared. Negative 72 plus 100 is going to be 28. Take the square root of both sides. Get x minus 10 equals plus or minus the square root of 28. So x equals, we'll do a little reducing here, 10 plus or minus, there is a perfect square in 28, 4 times 7, plus or minus 2 square root of 7. Now, ultimately, when you get the decimals here for this, you've got two approximations. So let me get them for you. So we have 2 times the square root of 7. So the square root of 7 times 2 plus 10 is 15.292. And then if I do the other one, 10 minus 2 times the square root of 7, you get approximately 4.708. Now, you'll notice before I did this that I said I wanted to look on the interval between 0 and 12. Where did I put that? Right here, right? Between values for x between 0 and 12. When you look at these two critical values, only this one is between 0 and 12. So I actually am not going to be looking at evaluating this volume at the 15 point something one. So I'm going to plug in my value. All right, so 4.708. So that's going to be, I think it was 4x cubed. Yep, 4x cubed. So 4 times 4.708 cubed minus 120 times 4.708 squared. I think it was plus 864x. Yes, plus 864 times 4.708. All right, so whatever that is will give me my maximum volume. All right, I'm going to go to Desmos to find that answer and just show you how a lot of this stuff you can confirm with your graph on Desmos, which is super nice. All right, so I'm going to type in, still use this one, 4x cubed minus 120x squared. There we go. And then plus 864x. Make a table if you would like. So you can zoom in. Not going to want to zoom in there because my x value is, I'll say 5. Because I care about the one that's at 4. I can zoom over and kind of see what's happening between 0 and 12 is my max. Look at there. Okay. So if I look at my maximum, it's right here. You already know the x value is 4.708, right? We found that approximation. So here is my maximum volume at that side length of square that's cut out of this cardboard box, 1,825.297. And it's going to be cubic feet, I believe. Is this in feet? I'm not sure. Inches, cubic inches, my bad. So it's going to be 1,825.297 cubic inches. So this is my maximum volume using that side length. Okay, so that's it for this one. I'm going to move on to the next one. Okay, so for the next one, we're going to talk about this problem where we're trying to minimize travel time. So we have an island. So I'll draw a little picture here. It's not going to be great, but we have an island. Let's say island. All right, that is 2 miles due north of the closest point along a straight shoreline. So here is the shoreline. All right, and that's going to be 2 miles here. And it says we have a visitor, excuse me. Excuse me. A visitor is staying at a cabin on the shore. So here I'll put our cabin. That is 6 miles west of that point. So this would be 6 miles. Okay? And we're trying to figure out how to minimize the time it takes for the visitor to go from the cabin to the island. And the visitor is going to do this by running, a combination of running, and a combination of swimming. Okay, so essentially, at what point should the visitor stop running and start swimming to minimize the time it will take to reach the island? All right, so there's a lot going on here. So essentially, we're going to have some value for x. All right, we'll call this x. That's the time it takes, or the time the visitor is running. All right, and then essentially, they're going to get into the water. Let me actually write this here. So this right here is the running, and that's going to be x. And then in terms of the swimming, that's going to be the letter y. All right, so they jump in the water and they start swimming. Okay, so if this is going to be x, then this distance is going to be 6 minus x. So we'll be using that later as another distance in that triangle. Okay, and ultimately I want to minimize time, so I need to write an equation that talks about time. All right, so if you think back to your days in middle school, you remember that your distance that you can run or swim, or distance of doing anything, is the rate at which you do it times the time at which you do it. Okay, so again, that's distance equals rate times time. So time, right, if I move my rate to the other side with division, is the distance divided by the rate at which you do it. So we have two times here, right? We have the time it takes, or the time the visitor is going to be running. Let me put R there. So the distance they're going to run is x, distance in miles, divided by the rate at which the visitor runs, which is 8 miles per hour, and the time it takes to swim, which is going to be y, the distance the visitor swims, divided by the rate of 3 miles per hour. So my total time that I'm trying to figure out here is x over 8, that's the time in terms of running, plus y over 3, the time in terms of swimming. So that right there is excellent, right? That gives us the equation that we're trying to minimize. Unfortunately, right now I can't do anything about it because we have two different variables. But you'll notice that what I can do is I can figure out another way to look at my y, right? Because we have a right triangle that's happened in this drawing. So what I'm going to do now is I'm going to use this next slide to figure out what y is using my Pythagorean theorem. So I'm going to have 6 minus x squared plus 2 squared equals y squared. All right. So I'm going to go ahead and do a little bit of work here. I have 6 squared, which is 36. Multiply 6 times negative x and double it to get negative 12x. And then that's going to be plus x squared. Okay, and then that's going to be plus 4 equals y squared. All right, go ahead and add some like terms here. So x squared minus 12x plus 40 equals y squared. Again, I don't want y squared, I want letter y. So when I want to finish this to get it to be y, I take the square root of both sides. I get the square root of x squared minus 12x plus 40. So what I'm going to do is I'm going to replace that. So t, my time, is equal to x over 8 plus, but instead of writing my y over 3, I'm going to write all of this, the square root of x squared minus 12x plus 40 over 3. Okay, so this is the function that I'm going to be trying to minimize in terms of my time. Now, before I go into finding the critical points here, you want to think about what values you're going to be using for your x. So when I look at my drawing, you'll notice that the total distance in terms of x, in terms of that's for how far the visitor is running, cannot be more than 6 miles. So I'm looking for values between 0 and 6. So over the interval between 0 and 6. So I'm going to plug into this real quick. I'm going to plug in t of 0 and plug in t of 6. I'm actually going to use decimals to help me here because there's a lot of pieces going on. And then I'll use that last slide to find my critical points. So we have t equals, and I'm going to just type in after the equal sign, we have x over 8, and then plus another fraction, the square root of x squared minus 12x, I think it's minus 40, let me confirm, I think it might be plus 40, all over 3. I'm going to make a table, and I want to figure out what happens when my x is 0 and when my x is 6. Right here. Okay, so when I have the x is 0, right? When x is 0, that means the visitor is not running at all. They're swimming the whole way. The time it takes is 2.108 hours. So that's 2.108 hours. And then when they have a time of 6, let's go to, where am I going here? Nope. Yes, that's what I want. For a time of 6, they run the full length of 6, and so they're just swimming the 2 miles up. That's going to be 1.417 hours, all right, approximately. All right, so now I'm going to find the critical points. So find the derivative of this t time function. So we have t prime. The derivative of x over 8, that's really like 1/8 times x. So that's just going to be 1/8, all right, plus, now this can get a little tricky here. Let me rewrite something for you real fast up here. So that'd be like the square root of x squared minus 12x plus 40 to the 1/2 power, and it's divided by 3. So I'm going to put the 1/3 up there. So if I do the derivative here, that's 1/3 times 1/2, which is 1/6, times x squared minus 12x plus 40 to the negative 1/2 power. But chain rule, you have 2x minus 12. Okay? So now I have 1/8, and then this is going to be plus, we have 2x minus 12 over 6 times x squared minus 12x plus 40 to the positive 1/2 power. So that's what the derivative is, okay? And ultimately, when I move, or when I set this equal to 0, I can move the 1/8 to the other side and get this proportion, and I can set up to solve this. All right, and I'll bring it back to square roots. This is going to be, let's do negative 6 times the square root of x squared minus 12x plus 40 equals 8 times 2x minus 12. Okay, now, in order to get rid of this square root, I'm going to square everything. So I'll show you with my algebra here, something that we did a couple years ago in Algebra 2. So you got to square everything. That's going to make the square root go away, but that is going to leave you with 36 times x squared minus 12x plus 40. And that's going to be 64 times 2x minus 12 squared. Okay, so let's do some algebra here. 36x squared minus, get my calculator here. That's 36 times 12, which is 432. And then 36 times 40 is plus 1,440. Then I have 64 times, that's going to be 4x squared minus 48x plus 12 squared is 144. Getting pretty big numbers here. At any time, right, if you get tired of doing something like this, you can always just type in, where was it? Right here. You could type this in to Desmos, and you could figure out where it hits the x-axis. That's the beauty of Desmos. All right, and that's going to be 64 times 4, which is 256 x squared minus 48 times 64, which is 3072x, and then, oh my goodness, this is a big one here, 144 times 64, which is 9216. Okay, so let's get all this set equal to 0, and then I can type it into Desmos. All right, so we have, I'm going to move this 36x squared over, get 256 minus 36, which is 220x squared. Then I have adding 432x, so 3072 minus 432 is going to give me negative 2,640x, and then 9,216 minus 1440 is 7,776. So I'm not even going to try to factor this. I'm just going to type it into Desmos so it can show me what the x value is for these, right? And I can write down what my critical values are from this. So I'm going to type in 220x squared. Oh, you know what? I guess we can just real quick show you. Right, this is the derivative. Is this derivative? No, this is not the derivative. We'll use this in a second, so I'll come back into that. And then we'll have the, it was 220x squared minus 2640x. Was that right? Let's see. Yep, plus 7,776. Get a table for this so I can see where in the world this is happening. Okay, so it looks like it crosses in two spots. 5.191 or 6.809. Now remember, I know we've done a lot of algebra since then, but remember I said we have to be looking for values between 0, let me get this correct here, between 0 and 6. All right. So in this case, I have my two values, my critical points, but one of them is outside 6, right? 6.809 is outside of that. So I'm only going to be using 5.191 as my critical point. So x is approximately 5.191. All right. And if I evaluate this time, I'll come back over here and do 5.191. Now I can go to my other function that I typed in and see what that time would take. So that means if this is what I end up doing, then the visitor would be swimming for would be running 5.191 miles out of those 6. So let's go to Desmos. Let's put this away. Let's bring this back. Let's do another one here. So 5.191, which is 1.368. And you can already see that 1.368 hours is smaller than the other two endpoints. So now we'll get it graphically. So hopefully this makes some sense in your mind. And there it is, 5.191. So that right there is the distance that we're telling this visitor to run before they get into the water and swim to the island. Okay, so that was a lot for this question, but ultimately we found the answer. Let's move on to a maximizing revenue question. Now this question about maximizing revenue, we're going to end up looking at finding the equation for revenue for this rental car company and then trying to figure out the critical points or the endpoints wherever it has the price we select that's going to maximize the amount of revenue for this car company. So they tell us that this rental car company has determined that if they charge their customers P, so the price P, dollars per day to rent a car, where the price is between $50 and $200 a day, the number of cars they rent per day, N, can be modeled by the linear function N equals 1,000 minus 5 times the price that they charge per day. If they charge $50 per day or less, they'll rent all their cars. If they charge $200 per day or more, they won't rent any cars. So that's kind of telling us that we have to choose a price that's between $50 and $200. And if we want to do that, what price should we tell them to use to maximize their revenue? So this really comes down to understanding how to find revenue. And revenue in this situation is going to be the number of cars, so N, the number of cars that they are able to rent per day, times the price that they're charging each customer to rent their car per day. So essentially, based on what they told us, N is the same as 1,000 minus 5P, and then times whatever price they're choosing in terms of charging their customers per day to rent a car. So if I multiply this out, our revenue is 1,000P minus 5P squared. Okay, now we want to maximize this, all right, and it tells us that we're using the interval between either $50 per day or $200 per day. So I'm going to first start off by evaluating this at 50 and at 200. All right, so I'm going to use my calculator for this. This one isn't as complicated as the previous one. So I have 1,000 times 50 minus 5 times 50 squared. So that's going to be a revenue of $37,500. Let's try 200. So 1,000 times the price per day of $200 minus 5 times 200 squared. That's actually going to be $0, which makes sense because in the problem, remember it says if they charge $200 per day, so right here, if they charge $200 per day, they will not rent any cars. So that kind of makes sense why I got 0 for the revenue. If you don't rent any cars, you can't make any money. Okay, so now let's use the next slide where I'm going to find the derivative of my revenue function. So the derivative of 1,000p is just 1,000 and then that's going to be minus 10 times p to the first power. So I want to figure out what makes this become 0. So 1,000 equals positive 10p. So the price we are looking at is 1,000 divided by 10, which is $100 per day. So let's evaluate the revenue function at 100. So that's going to be 1,000 times 100 minus 5 times 100 squared. All right. So we have 1,000 times 100 minus 5 times 100 squared. And that's going to be a revenue of $50,000. And if you compare that to the revenue that we looked at for the endpoints, obviously we're not using 200 because that gave us $0 of revenue. We didn't sell or we didn't rent a single car. But if we use $50 a day, we'll rent all our cars and we'll make $37,500. But if we use a price of $100 per day, I don't know exactly how many cars we would actually rent. I guess I could plug it into this real quick. Let me see. So N at 100 would be 1,000 minus 5 times 100. That's 1,000 minus 500. That'd be 500 cars. And if we chose 50, let's see, 1,000 minus 5 times 50, that's 250, that's 750 cars. So there's a total. You don't really need to know this for the problem, but I'm just curious in terms of like if this was real life. This company has a total of 750 cars. So if we stop saying sell, Douglas, if we rent our cars at $50 a day, in theory, we will rent all of these cars. 750 cars will get rented because the price is so low. All right, but we only make $37,500. If we price at $100 per day, we're not going to rent all of our cars. You'll notice that we're talking about only renting 500 of the 750 cars. But because our price is set to maximize revenue, we end up actually making $12,500 more dollars, even though we didn't rent 250 of the total 750 cars that we have. Okay, so one of those things just give you a little context about this problem. All right, so I'll go ahead and show you in Desmos so you can see all the work we did with the calculus and algebra, that you can do a lot of it with your graphing utility. So I'm going to type in, let's delete all this, 1,000p x minus 5x squared. And we were looking at in between 50 and 200. Let's see, what do we end up using? We end up using 100. Let's delete all these. Okay. And here you go. Here's what it looks like. So where's 50? 50 is here. Remember, we would make $37,500 for our revenue. There's 200. Revenue is nothing. And here is where we maximize revenue at a price of renting a car per day of $100. All right, so that is that problem. All right, let's keep moving. Got 2 more to do. I know I've got a lot going on here. 2 more, and then we'll be done. Maximizing the area of an inscribed rectangle. Okay, so we are going to work on this problem of maximizing the area of an inscribed rectangle. Now, this does require a little bit of an understanding of what an ellipse is, and I'm going to go ahead and graph that for you in Desmos to show you just what this ellipse looks like. So we have x squared over 4 plus y squared equals 1. And I want to make sure you can actually see it. Let me zoom in a ton here. Almost there. I need to change my y-axis. Is way too big here. So let's go -4 to +4. There we go. Zoom out a little bit. Okay, so you can see the ellipse here. Let me do actually -3 to 3. There we go. All right, so you can see the ellipse, and we want to put a rectangle in this ellipse that maximizes the area of the rectangle. So you can visualize some rectangles in here, but ultimately I wanted to show you this ellipse because we didn't really get to do it a couple years ago when you guys were in my class for Algebra 2. I'm going to blame this on myself as well as the pandemic because normally we would have gotten a section on some conic sections. So here's an ellipse. It's the reason that it looks like this. We call this a horizontal ellipse is because you'll notice the denominator underneath x is 4, and the denominator underneath y squared is 1. It's not there. So that means we're going up and down 1 unit, and we're going left and right the square root of this denominator, which is 2. So that's why we're going to -2 to +2. Anyway, you don't really need to know a ton about this, but that hopefully should help you a little bit in terms of when I draw this sketch. So I have an ellipse. Okay, so an ellipse, and it's a horizontal ellipse, where this is going from +2 to -2, and we're going up to +1, down to -1, and we're drawing a rectangle in here that is going to maximize the area of the rectangle. Okay, so essentially what we're trying to do, all right, is I'm trying to write the area in terms of this rectangle first. Okay, so I'm going to write down the area is length times width. All right, and what I'm going to do to help me figure this out is I'm going to focus on a point. All right, and that point is in the first quadrant. So this point right here. So once I do that, essentially what I'm saying is that when I write my length here, all right, when I write my length is going to be, if this is x and y, my length is going to be 2 of these x's, right? If this is my length, that's going to be 2x. And my width, which is like this, is going to be 2 of those y's. Okay? So my area is going to be 4xy. Now, unfortunately, I can't really move forward with this because I have 2 variables. So what I want to do is I want to use this ellipse equation up here and solve for y. So y squared equals 1 minus x squared over 4. Taking the square root of both sides, you get y equals, right here, y equals the square root of 1 minus x squared over 4. Okay, so I'm going to replace that, and to get 4x times the square root of 1 minus x squared over 4. So this is essentially the equation that I want to find the maximum of, or maximize this equation, this area. So I'm going to plug in, let me talk about the endpoints. I'm looking at my x values. You'll notice that in terms of the x-axis, the farthest right and farthest left I'm going is -2 and +2. All right, so in terms of my domain here, because I need a positive value for x, my interval that I'm looking at is between 0 and 2. So I'm going to plug in my endpoints of 0 and my endpoints of 2 into this area formula. So I get 4 times 0, which is 0. 0 squared, 0, 0 over 4, 0, 1 minus 0 is 0. 1 minus 0 is 1. Square root of 1 is 1. But 1 times 0 is still 0. Plugging in 2, I get 8 in front. 2 squared is 4. 4 over 4 is 1. 1 minus 1 is 0. The square root of 0 is 0. But 8 times 0 is 0. So essentially my endpoints are not going to be in my maximum area. So I need to find the derivative of my area. So let's write that down. Here's 4x times the square root of 1 minus x squared over 4. Okay, so I'm going to find the derivative. This is going to be using the product property that we practice so much. The derivative of 4x is 4. So times the square root of 1 minus x squared over 4. And then plus the derivative of this square root, watch how I do it, it's going to be 1/2 times 1 minus x squared over 4 to the negative 1/2 power times the derivative of inside. The derivative of 1 is 0. So the derivative of negative 1/4 x squared is going to be negative 2/4 or negative 1/2 x to the first power. Don't forget to multiply times the other one, 4x. All right, so there's a lot going on here. Let me make it a little nicer. So that's 4 times the square root of 1 minus x squared over 4. And this is going to be plus, let's see, what's going to go in the numerator? In the numerator, I have, let's write minus because we have subtraction or have negative in there. So minus, I'll have this 4 way over here, and this 1/2 and 1/2, right? That's 1/2 times 1/2, which is 1/4, and 1/4 of 4 is 1. So it's just going to be, looks like negative x over the square root of 1 minus x squared over 4. Okay, make sure I got all that. I think this is going to be x squared. Let me make sure that. So the 1/2, 1/2, and the 4 becomes 1. The negative x times x is x squared, so that's good. I caught that mistake. And then we're going to go. So now what I'm going to do is, since this is equal to 0, I'm going to set up a proportion that has x squared over the square root of 1 minus x squared over 4 equals 4 times the square root of 1 minus x squared over 4 all over 1. When you cross multiply, you get x squared equals. Now watch what happens here. You have 4 times. When you multiply a square root times a square root, the square root is going to go away. So you have 1 minus x squared over 4. I'm going to distribute to get 4 minus 4 over 4 becomes 1, so minus x squared. Moving the x squared to the other side, you get 2x squared equals 4, or x squared equals 2. So x is equal to plus or minus the square root of 2. Now, remember the interval here, right? Plus or minus the square root of 2. I don't want to do the negative version because my values for x are between 0 and 2. So my critical point is the square root of 2. Okay, I do have one more slide. Excellent. So I'm going to plug in the square root of 2 into my area function. So a of the square root of 2 is 4 times the square root of 2 times 1 minus the square root of 2, all of that squared, over 4. So that's 4 times the square root of 2 times, let's see, square root of 2 squared is 2. 2/4 is 1/2. 1 minus 1/2 is 1/2. That's the square root of 1/2. Okay, you can put those together. So that's the square root of 2 times 1/2. Half of 2 is 1. Square root of 1 is 1. So that gives us an area of 4, which when I compare that to areas of 0, I know that that maximizes my area. So the value for x we should use is the square root of 2. Now, I'm not done because I need to find the dimensions for this. I told you that my length was 2x and my width was 2y. So the length is pretty straightforward. That's just going to be 2 times the square root of 2. All right, and then for my width, it's 2 times, and remember we said y was the same as the square root of 1 minus x squared over 4. So that's 2 times the square root of 1 minus x squared over 4. That's 2 times the square root of 2 squared is 2. 2/4 is 1/2. 1 minus 1/2 is 1/2. So this is going to be my width that I have. All right. And let me make that a little nicer. The square root of 1 is 1. So that's 2 over the square root of 2, which if you wanted to rationalize the denominator, it would be 2 square roots of 2 over 2, which is just the square root of 2. So here's my length, and here is my width. Okay, and my maximum area is 4 square units. Are there any units here? Nope, it's 4 square units. Okay, so there it is. That's the whole problem for maximizing this area in this inscribed rectangle inside an ellipse. Okay, we got one more. Oh my gosh, guys, we're so close. If you've made it this far, good on you. We got one more that minimizes the surface area. Okay, so for our last one, we're going to be minimizing the surface area here. And the only thing that makes this a little bit trickier is that we're not going to have a closed bounded interval like we have for the first 5. So on this one, you'll see that we have an unbounded interval. Value just has to be x is greater than 0. And you'll see, again, we'll do the algebra with the calculus, but I'll show you on Desmos as well to kind of show you. There's a simpler way to do this without doing all the algebra. So we have a rectangular box with a square base. Okay, so rectangular box with square base. So we have our open top and a volume of 216 cubic inches to be constructed. All right, so we have, let's see, what do I want to use for my letters here? I'm going to have X for this one, and then I'm going to have an X for this one, and then Y for my vertical one up there. So I need to find the surface area of this box. So the surface area is going to have, if I look at the vertical ones, I'm going to have X and Y as the area of those rectangles. So that's going to be 4 of them, right? There's 4 vertical faces, 1, 2, 3, 4, that are facing, we count 1, 2, 3, and then on the backside. So that's 4 times X and Y. And then plus, I just need the area of this base because we said the top is open. So the base of the area, or area of the base, is going to be X times X, which is X squared. Now, I'm not ready to take the derivative and figure out what the minimum is just yet because I have 2 unknowns. But what I can do is I can figure out a way to rewrite Y using X. And in terms of the volume, that's going to be X squared times Y, right? Because X times Y, length times width times height for the volume. So, and that's the same as 216 cubic inches. So if I solve for Y, that's going to be 216 over X squared. Okay, so I'm going to plug that in for Y and get 4X times 216 over X squared plus X squared. So my surface area formula is going to be, let's see, 4 times 216. That's going to be 8 something. 4 times 216. 864. So 864 over X, because I have 2 in the bottom, 1 on the top, plus X squared. So this is what I'm going to be using in terms of finding critical points. Now, here's the thing that's different. At this point in the problem, what we've done in the past is we have looked to see what the bounded interval is and then use those endpoints first. But because it doesn't have, like a maximum value for X that I need to worry about, I just need X to be positive. So I'm just going to find the critical points and figure out what makes that derivative equal to 0. And that'll be the critical points. And hopefully that'll be my X value for the minimum. So I'm going to find the derivative. So that's going to be, let's see, 864 times X to the negative first power. That's going to be negative 864 times X to the negative second power plus 2X. Write that a little nicer here. Negative 864 over X squared plus 2X. I need to set that equal to 0. So if I move the 864 over X squared to the other side, I get 2X over 1. We have a proportion. I get 2X cubed equals 864, or X cubed equals 864 divided by 2, which is 432. So to find X, I take the cube root of both sides. So the cube root of both sides will give me my value for X. So X is, let's see, what is the cube root of 432? Cube root of 432 is 7.56 approximately. So approximately 7.56. Okay, so this is what I should use for X to minimize our surface area. And then to find Y, remember Y was the same as 216 over X squared. So to find Y, I'm going to do 216 over this 7.56 squared. All right, so let's see, 7.56 squared divided by 216, flip it. Where's my 1 over? It is. And you get 3.78, so approximately 3.78. So those are my dimensions that I should use. And then to minimize the surface area, when I use those, I'm going to plug in my numbers, which is 4 times 7.56 times 3.78 plus 7.56 squared. Now, you'll notice when I go to Desmos, I can get the exact answer here because so far I've been doing some rounding. And as any math teacher would tell you, you want to leave your rounding to the very end. All right, so I know I wrote my work is rounded, but I'm not going to do any rounding. I'm going to type in my stuff here, which is my equation for surface area was 4xy plus x squared. 4x, no, that wasn't it. What happened when I put on the y? There it is, 864 over x, 864 over x plus x squared. And I'm looking at values between, it was 0 and I think I had 7. So I think it was like something in 3 and 5 and 7. I'll do 9 as well. So this will show you where my minimum value is, which is right there, the 7.56, which remember I found approximately 7.56. So right here is 7.56 with the surface area being minimized of 171.439. 171.439. 171.439, and this is square inches. All right, so that's it, guys. I know that was a super long video. I totally understand. A lot of this stuff, once you end up writing the equation and getting it in terms of one variable, you can just go to Desmos, type it in, find the maximum or the minimum. So that's really nice. But I did want to show you the calculus and the connection between optimization problems and the work we did with derivatives, especially with critical points. So hopefully you see the connection between those two things.